Hello everyone. Today we're going to finish our discussion on the linear quadratic regulator. And as I've said previously, the LQR problem, for short, is it's essentially a fundamental problem in control theory, and it provides the building blocks for much more complicated problems. And the reason why I say it's relatively simple, just to expand a little bit, is because the systems we're dealing with are linear quadratic systems. Linear systems, sorry. And they look something like this, right? We have a linear system with the state matrix A and the control matrix B. And of course, our state is in Rn, and our control is in Rm. And this is for a discrete time system. We can also have for a continuous time system, in which case we'll have an ordinary differential equation. X plus b t. Okay, and so yeah, it's a linear system. And the problem is, that's good and all, but in real life, vehicles are not linear by nature. Like a rocket moving through the atmosphere is not going to be governed by no linear system. A drone moving, or a quadcopter or an aircraft, they're not going to be governed by linear systems. They're always going to be nonlinear. But we can employ different techniques, such as linearization, to turn it into a linear system. So that's what I mean by like a building block. You can turn something into a linear system with a quadratic cost function, and you can solve it via LQR. Another disadvantage of this system is that it's deterministic. It has no noise on the system. And that could be problematic as well, because in real life, of course, we're not going to be able to model our dynamics exactly. Sometimes we have good models, sometimes we don't have good models. But in every scenario, we're going to have noise on our system. It could be wind. It could be literally anything. Any disturbance that's not inherent to the system. It's called an exogenous disturbance. And then that's when you start getting into the realm of stochastic optimal control, which we're not going to get into. But okay, let's go with this system. And you know what? I'm in the mood for continuous time, so let's do continuous time. X dot equals a. I'm just going to write like this, a subscript t. X plus b subscript tu. X is in Rn, u is in Rm. And today we're going to finally finish solving this problem. And since this is the linear part, remember? And then we also have the quadratic. And what is that? Well, you guessed it, it's the cost. So the cost function that we want to optimize, or rather minimize, is going to be a quadratic function. Well, first we're going to have a terminal cost, 1/2 x, I'll call it xt transpose, let's say qt, and then xt, qt, plus the integral 1/2 integral 0 to t. And I should mention here that our time horizon is from 0 to capital T. So this is our terminal cost, because it's at the final time, terminal cost. And then we also have this running cost, which is also a quadratic in terms of x and u. There we go. Okay. So this is our terminal cost, and this is our running cost. And of course, it's quadratic in both the state and the control. Additionally, these weighting matrices Q and R, they could be time varying as well. The only condition is that Qt has to be greater, positive semi-definite, and R has to be positive definite for all time. Okay, so this is what we had already. We know this. This is the problem set up. And okay, how do we solve this? Well, we constructed this thing called the Hamiltonian. Which you can loosely think of as the energy of the system. And the Hamiltonian is defined as what's known as the Lagrangian plus the Lagrange multipliers times the dynamics. And okay, so just to review, this is the Lagrangian, and the Lagrangian is just the running cost, and these are our dynamics. So plugging everything in, we have 1/2 x transpose, and I'm just going to drop these subscripts because we could just put them back in later. So this is the Lagrangian, and then plus lambda. These are Lagrange multipliers, and then multiplied by our dynamics. And just to repeat, these Lagrange multipliers have the same size as the state. Okay. So we have our Hamiltonian. Nice. What's next? Well, from optimal control theory, and this actually comes from calculus of variations. So I haven't derived this, just to be clear, but it can be derived from calculus of variations. And these give the necessary conditions for a minimizing solution. Because our whole goal is that we want to minimize this guy. We want to minimize the cost subject to these dynamics. If you go through the calculus of variations, you end up with these necessary conditions for the optimal control that minimizes this cost function. And okay, what do these necessary conditions say? Well, the first one is that the derivative of the Hamiltonian with respect to the Lagrange multipliers is equal to f. And is this true? Sorry, well, you can write f, but it's more customary to write x dot. Is this true? What does this give us? Well, dh d lambda, since lambda only appears here, this is just ax plus bu equals x dot. So this is satisfied trivially, right? Okay, so that's just like a sanity check, I guess. The second necessary condition is that the derivative of the Hamiltonian with respect to the state is equal to negative lambda dot. And this is referred to as the state equation, and this is referred to as the co-state equation. And yeah, so these Lagrange multipliers, I've been calling them Lagrange multipliers, but they also have another name called the co-state. And it's because the state and the co-state, they have very similar dynamics, but they're kind of like dual to each other. They're kind of flipped, right? As you can see, the derivative here is with respect to lambda, but here it's with respect to x. So it's kind of like flipped. So it's co-state and state, whatever. Okay, so let's compute these derivatives. dh dx. Well, we have x here, and we have x here, right? So the derivative of this guy is just going to be a qx, because it's just a quadratic, plus, and then we'll have an a transpose lambda from the derivative here. So two derivatives, and this is equal to negative lambda dot. Okay, so we have one equation already. That was a terrible box. Okay, and now for perhaps the most important one, this is called stationarity. This is the stationarity condition. And what it says is that the derivative of the Hamiltonian with respect to the control or to the decision variables is 0. And that's why it's called stationarity, because the derivative is 0. So, okay, what is the derivative with respect to the control? I'm running out of colors here. But as you can see, we have one here, one term here, and one term here. So, taking the derivative is going to give us RU from the first term plus b transpose lambda from the second term. And this is, of course, equal to 0. And so we immediately see, this is a u, we immediately see that the optimal control is given by just rearranging terms, doing some algebra, is given by this. Beautiful box. I redeemed myself. But yes, so this is the optimal control. And give me just 1 second to drink some water. Okay, so we found the optimal controller, but there's still a problem, right? Because this is a function of lambda. And we don't know what lambda is just quite yet. We know that it satisfies this differential equation, but we don't know what lambda is specifically. So how can we get around this? And here is where I give you an argument for why the solution is what it is, and then we'll see why. And the argument goes like this. Let me just drag this over. So let's assume, oh, and before I get into that, there's one more thing that I forgot to consider. And this is called the transversality conditions. Transversality. And transversality comes from the fact that we have a terminal cost. So if we just had this running cost and that's it, we would just have these three conditions and that's it. Since we have this terminal cost, we have an extra condition, which is called the transversality conditions, and it says that the derivative of the running cost, phi, I'll call it, with respect to the state, is equal to, the derivative of the running cost with respect to the state evaluated at the final time is equal to the co-state at the final time. And what is phi here? Well, phi is just the terminal cost. I just denoted by phi. And of course, it's a function of both. It could be a function of the terminal. It could be a function of the state, and it could also be a function of time. Okay, so this is a terminal cost. And since we do have a terminal cost, we have this last condition called the transversality conditions. And what does this become? Well, d phi dx is just qt. This is the terminal weight times x t. And this is equal to lambda at the terminal time. Okay, so these are the transversality conditions. And the reason why I need to mention this is because now in our assumption. So let's assume that lambda of t is equal to some function p of t times x of t. Let's just assume this a priori. The reason why I'm assuming this is because I already know that at the final time, at lambda of t, at the final time, I should write parentheses t here, I know that at the final time that the co-state is equal to q times x. And so I can backtrack a little bit and say, okay, if it's equal to this at the final time, what if it's equal to this at any arbitrary time t, for any t, right? Not just the terminal time or the final time. So let's just assume this, and let's see what happens, because why not, right? So let's take the derivative. Lambda dot is equal to, well, now we have to do the chain rule, because p and x are both functions of time. So chain rule says p dot x, plus px dot, just by the chain rule. But we know x dot. So this is equal to p dot x plus p times ax plus bu. These are just the dynamics. That's what x dot is. Okay, let's keep going. What is u? Right? You see what's happening here. We're turning everything into a function of x. So let's keep going with it. What is u? Well, u comes from right here. So let's plug that in. Equals p dot x plus, and now I'm just going to expand it a little bit, p times a times x plus p times b times u. And now I'm going to plug in u, p dot x plus p ax plus pb. And now, okay, what is u? U is negative r negative 1 b transpose lambda. But like we can keep going even further. What is lambda? Well, lambda is given by this guy. This is our assumption, right? Equals p dot x plus p ax minus, pull this negative sign out, pb r negative 1 b transpose. And now what's lambda? Lambda is just px. And now we see what happened here. Well, we have an x here, and x here. So we can put this all together. We get p dot plus pa minus pb r negative 1, boom, boom, boom. And this is all times x. So lambda dot is equal to something times x. But we know what lambda dot is from here as well. So let's plug this guy in. We know lambda dot is already equal to this guy, and we already know lambda is equal to p times x. So what this guy is saying is that negative lambda dot is equal to q plus a transpose p times x. Right? Because this is, again, they're both functions of x, linear functions of x. So, okay, let's plug this in to the left-hand side of this expression. And what do we end up getting? Well, negative lambda dot is equal to this. So this is equal to negative q plus a transpose p x is equal to the right-hand side. P dot plus pa all of this. Okay? And this must hold for all x in Rn, let's say. This equation holds and must hold for all of x. And so we can kind of cancel these x's out in a way. But a lot of people do this, but they don't explain why we can do this. And the reason why we can kind of cancel the x's is because this equation must hold for all x. And so if it must hold for all x, that means that the left-hand side must be equal to the right-hand side. So that's kind of the rough explanation. So setting these two equal to each other, we see that P actually solves a differential equation. What is this differential equation? Well, I'm just going to rearrange some terms over here, but it ends up being something like this. So we're going to get negative P dot is equal to PA plus A transpose P minus this guy plus Q. So we assumed, I need to get this square because this is an important equation. There we go. Okay, so let's just backtrack real quick. We had this assumption on the costate that it's a feedback, it's a linear function of the state. We took the derivative and we set the left-hand side from before equal to the derivative. And we got this differential equation for P. And this is a very special equation, and it's known as the Riccati equation. Riccati equation. It's actually known as the differential Riccati equation because of the derivative. And there's also another version of the Riccati equation called the algebraic Riccati equation. There's also discrete time and continuous time algebraic Riccati equations, but whatever. So this is the differential Riccati equation, and notice that it's a quadratic in P. So it's something like, you can imagine x dot is equal to something times x plus something times x squared. So it's a quadratic in P. And it's also non-homogeneous because of this plus Q here. So there's one more thing to consider here, and that's every differential equation. This is an ordinary differential equation. Every differential equation has to have boundary conditions. It has to have some kind of initial or terminal condition. And we see that from exactly here. And from this, we see that this matrix P at the terminal time has to be equal to Q. So we have a differential equation for the Riccati matrix P, and it has a terminal condition. So the way that one goes about solving this, at least numerically, let's say for example in MATLAB, is that you start off with the terminal condition, that's your initial condition, and you propagate it backwards in time. So this is called a backwards differential equation because the constraint is at the terminal time. That's why it's called a backwards differential equation. If it would be called a forwards differential equation, we would have a condition such as an initial condition where P of 0 is equal to some Q of 0, right? But this is not the case here. This is a backwards differential equation. So if we want to numerically solve it, we have to start at the terminal time and move backwards. So just a little background on this equation. But the great thing about this is that we solved the problem. And you may be asking, how do we solve it? Well, let me just recap. So our optimal controller that we found from stationarity was equal to negative R inverse R B transpose lambda. B transpose lambda. And remember, we said that lambda was equal to P times X. And we already know P. We can find P from the solution of this differential equation with this terminal constraint. So this is our optimal controller. U star is equal to this. And we solved the problem. We have solved the LQR problem, and we found the optimal controller U that minimizes the cost J. And it's the surprising thing here, and this is like the hallmark of LQR, is that the optimal controller controller is feedback. It's a feedback controller. And that's pretty cool because feedback controllers are generally more robust than just open loop controllers. So the optimal controller that solves the LQR problem is a feedback controller. It's a linear feedback controller. And it's a function of this matrix P, which is the solution of the Riccati differential equation. So there it is. I hope that was clear and it made sense. And next time we can even start looking at tracking problems. The reason why it's called a regulator is because implementing this controller will stabilize the system to the origin. It's going to stabilize it to the origin no matter what. It might look different for different systems, but it's always going to stabilize to the origin. That's why it's called a regulator, origin. But in many applications, you want to hit some kind of like set point or waypoint, for example. So let's say you start off at the origin and you want to hit this waypoint over here. Let's say at 5, right? And you want to hit this waypoint. So this will be referred to as a tracking problem. And tracking problems, you can do LQR tracking. It's pretty easy, essentially. It's the same thing as we've been doing, but it's just slightly different, just very nuanced. But we can do that next video. And we can also do output feedback. And what this means is that instead of having just the dynamics, we also have some output. And it can be in general some linear function of x and u. And this output could be, for example, measurements on the system. So let's say you have like a rocket going to space, and your state is like the position and attitude. It's a 12-dimensional state. But in reality, the measurements that you're going to get are from sensors, like accelerometers, gyroscopes, even GPS. And so the measurements do not have to be the same as the state. And so then you get this problem of LQR with feedback. And this is where we get into things like the Kalman filter and really interesting stuff like that. But okay, so here we solved the LQR problem, and we got this feedback controller, and we've talked about the Riccati equation, how it shows up. So thanks for watching.